You have already seen this product. You've probably watched the unboxing and the basic tools. So today I am skipping all that. Instead, I wanted to show you something different with this scope. Some practical tips and insights that you might actually find useful. Let's start with the design. Right out of the gate, it's a good looking piece of kit. The combination of 4 physical knobs and a respective touchscreen makes navigating through menu and settings a surprisingly pleasant experience. But I am not just going to tell you that. Later in the video, I'll give you a live demo of exactly how that plays out in the real workflow. And that's just the beginning. I'll also cover a handy power saving trick, like how to disconnect the internal fan. And we will break out the thermal camera to see which component really heat up under pressure. So stick around, let's get into it. Now let's look at my setup. The manual states the 2D15P can do 100 MHz on one channel or 50 MHz when both are active. Frankly, testing those limits isn't what I am after today. Instead, I am more curious about its performance at the other end of the spectrum, measuring very low frequencies, from 0 to about 10 Hz. How does it handle these slow signals, especially compared to a much cheaper oscilloscope? That's what we are going to find out. For this test, I'll use my oldest signal generator, starting at 8 Hz. All scopes display the frequency correctly, or very close to it. Now down to 6 Hz. We are starting to see a slightly discrepancy in the reading on our subject. And as we approach 1 Hz, the problem becomes more pronounced. The 2D15P begins showing widely different values for that 1 Hz input. Believe me, I did my due diligence, checking connections. The scope consistently fails to look onto and display the exact low frequency, even when using its own internal signal generator for a loop back test. The results are the same. So what's going on here? After some research, this turns out to be a classic symptom of interference when dealing with very low frequency signals. A 1 Hz waveform is so slow that the scope's trigger circuit can get confused, latching onto electrical noise or harmonic instead of the actual signal. What's the solution with this scope? We have to bypass the automatic frequency counter and measure it manually. Activate the X-axis cursor and carefully place them to capture one full period of that 1 Hz signal on the screen, like so. By measuring the time between these two cursors, we can calculate the frequency ourselves. This method will give you an accurate measurement. So, for very low frequencies, don't pay attention to the automatic readout at the top. Trust the manual cursor measurement instead. Moving on to our next topic, the on-screen display. If you haven't noticed it yourself yet, let's talk about a key usability issue. The measurement readouts are simply too small. The font used for numeric values and measurement labels on the oscilloscope's screen is somewhat undersized. Adding to the problem, the decimal points between numbers are minuscule, appearing to be only about 1 pixel in size, as you can see here on the screen. This lack of visual clarity can slow you down when you are trying to analyze data quickly. I actually reached out to the company team about this specific concern. I sent them an email detailing the issue, and they did respond. They stated they would pass the feedback along to their appropriate software team. Alright, our next topic, on-screen noise or parasites. If you power on the scope and immediately see this kind of interference on the display, this is often caused by having the oscilloscope plugged in and charging via its USB-C port. It's important to note this doesn't happen with every charger or power source, but with certain ones. It introduces significant electrical noise onto the display. The fix, however, is very straightforward. If you need a clean signal for precise measurements, simply disconnect the USB-C charging cable from the oscilloscope. The interference should disappear immediately, giving you a much clearer baseline. Next up, let's talk about power consumption. To measure this accurately, I've connected a used power meter between the scope and its charger. As you can see on the display here, the scope draws approximately 1 amp at 5 volts, which translates to a power consumption of about 5 watts. Next, power saving modification, disconnecting the internal fan. I noticed during testing that the scope's battery could drain significantly in under 2 hours of normal use. This made me wonder, is the interior actually getting hot enough to require active cooling? To find out, I opened the unit and took a look with a thermal camera. The result was clear. Under the conditions I tested, it simply wasn't the case. The components weren't generating enough heat to necessitate the fan. Since the fan wasn't critically needed for my use case, I found it can be disconnected quite easily. Doing so saves approximately 100 milliamps of current draw and, as a bonus, completely eliminates the fan noise. Finally, let's cover some other useful features and information. First, the charging indicator. When connected to external power, a red LED means the battery is charging. When the LED turns green, charging is complete. Signal recording and analysis. To record a signal for later analysis, first capture multiple periods of the waveform. You can do this using either the run stop button or the single button to capture a one-shot event. Run. This is your main control to start and halt acquisition for the scope, multimeter and generator. It has a green light for run and a red light for stop. "50% button", a great shortcut. Press it to instantly set the trigger level and channel offset voltage to their midpoint. It also centers the trigger delay time. Trigger and layout. The trigger system has 4 direct access settings for quick adjustment. Also, take note of this area of the screen. It shows 4 small status windows for channel 1, channel 2, the waveform generator, and the multimeter, giving you a complete system overview at a glance. Save button. Pressing this lets you take a screenshot of the current display. To access your saved screenshots, press the menu button, then click Picture. From there, you can select a screenshot to view your captured image or delete them if needed. A simple press to the back button will return you to the main menu. Location the reset button. Now you might be wondering, where is the reset button? It's right here on the right side of the unit. You'll see a small pinhole. This is the factory reset button. You say slow